Hello guys, and welcome back to my videos. So in this video series, I'm for applied machine learning, I'm going to be showing you how to use machine learning for real world cases. So in this scenario, we have credit card fraudulent transaction. So we'll be trying to use machine learning to detect fraudulent transaction. So I got this dataset from Kaggle. So this dataset presents transactions that occurred in 2 days, where we have 492 frauds out of 284,807 transactions. So you can see that the dataset is highly unbalanced. The positive class, which is frauds, account for 0.172 of all the transactions. Uh, the dataset also only contains numerical input variables, which are a result of principal component analysis transformation. So due to confidentiality issues, we were not given the labels of these features. They were just labeled V1 up to V28, and since they went under principal component analysis. So before principal component analysis is done, so these features have already been scaled by the Keiko team, or the source of the data provider. So our goal in this dataset is to identify fraudulent transaction, and there's other thing that we should note. So in this case, we are dealing with a imbalanced data sets. We can see that we have 0.172 of all transactions are frauds. So we can see that the number of non-fraudulent transactions is way too big than the number of fraudulent transactions. So I'm going to show you how to use other techniques such as random undersampling and random oversampling to create a subset of the dataset that contains equal distribution of fraudulent transaction and non-fraudulent transaction. So also note that since our dataset is imbalanced, we do not use the accuracy matrix. So we will be using the area under the precision recall curve, and then we also the confusion matrix is not meaningful for an imbalanced classification. So the first step we are going to do is we are going to import our dependencies. We are going to import NumPy, which is also used for mathematical operations. If you are familiar, we are going to import TensorFlow, which is a library used to create neural networks. And then we are going to import Matplotlib, which is a library that we use for visualizations, as well as Seaborn. We also use it for visualization. And then we are going to import sklearn libraries. So sklearn libraries use them for performing principal component analysis, and also they have traditional machine learning algorithms such as logistic regression, the support vector classifier, k-nearest neighbor classifier, decision tree classifier, random forest classifier. So if you are not familiar with any of these algorithms, you can watch any of my previous videos. I've explained how the logistic regression work, the support vector classifier, the k-nearest neighbor, the decision tree, and also the random forest classifier. So we have also other libraries such as the model selection, where we're going to implement the test split that we use to split our dataset into test set and then into training set and test set. And then we are going to import also the pipeline. If you are not familiar with the pipeline, I also recommend that you watch my previous videos on where I explained how to use the sklearn pipeline. So the next thing is I'm going to load this CSV file that contains our credit card information. So I've stored this file on my disk. So the next thing is I'm going to use pandas, which is a library that we use for pre-processing. So here I'm going to use the data frame df, which I define as df is equals to pd.read.csv, and then in that read csv file I'm going to pass in my dataset, and then the df.head is going to print out the first five rows in my dataset. As you can see, I think the computer is still processing. Okay, let's wait. So as you can see, my columns, I have the time. So I have V1 up to V28, and we're also given the time, which is the time in which the transactions occurred. and also we are also given the amount of transactions that were the amount of transaction that we okay, and then we have the class. So the class 0 represent a non-fraudulent transaction, and class 1 represent a fraudulent transaction. So this is what we call a binary classification situation, where one represented a positive outcome, which is fraudulent transaction, and 0 represents a negative outcome, which is a non-fraudulent transaction. Okay, so in the next we are going to have the df.describe, which is going to give us a description of our data set, which is going to give us a description of our data set. As you can see that the minimum amount of transaction, the mean of the transaction, as you can see, this is the mean of the transaction, is $88.34. So as I will visualize the graph, you will see that this data set, in terms of the amount of transaction, is rightly skewed, is skewed to the right. Okay, so the next thing is we are going to see if we have any missing values. So on Kaggle, they say that there are no missing values for this data set. So the df.columns will show us all the number of our columns. So the next thing now is I'm going to print the overall how our data set is. So we are going to show the no frauds, the class. We are going to print the class of the non-fraudulent transaction and the class for the fraudulent transaction. As you can see that non-fraudulent transaction accounts for 99.83 of the dataset, and fraudulent transaction accounts for 0.17% of the dataset. So if we use this dataset as it is, our algorithm will overfit our dataset. So every time we use our algorithm, if we want to detect fraudulent transaction, it's always going to give us an outcome that a transaction is non-fraudulent, right? So there should be a scenario. So there should be a solution to this. So a solution to this is to create another subsample of our entire dataset that is the equal number of classes. So that is a balanced equal number of classes. So we can also print the visualization of this graph. As you can see, for our positive classes, you can see it's negligible as compared to our non-positive class, right? So in our dataset, we saw that they told us that the features v1 up to v28, they went through principal component analysis, right? So before principal component analysis done, they first scaled all the dataset. So the other columns, which is amount in time, those are the only columns that are not scaled. So we need to scale those columns, right? So here we are going to print the distribution of time and distribution of transaction amount. So as you can see, we say that our mean was around 88, which is somewhere here, and as you can see, our data set is skewed to the right. It's skewed to the right, or it's positively skewed. So if you're not familiar with skewness, you can check my videos. I have some videos on skewness, right? And if we take the distribution of transaction time, we can see that there's a time where the number of transactions were declining, as you can see here. So we assume that the number of transactions were declining during the night when people are asleep, right? So now the next step is we are going to import from scikit-learn the standard scaler and the robot scaler. So the robot scaler, the advantage of using the robot scaler is the robot scaler is less prone to outliers, right? So now we are going to initialize the standard scaler class. Std scaler is equals to std. We create an instance of the standard scaler class, and then we create the instance of the robot scaler class, and then now we'll create another column in our dataset, which we are going to say scaled amount and then scaled time, which we are going to call scaled amount and scaled time. So in those columns we are going to then fit our transformed values or our scaled values. So here df scaled amount is equals to Robert scalar dot fit and transform. We want to fit and transform the amount column, and then we reshape the values from -1 up to 1. And then here we are going to fit and transform the time column and reshape the values from -1 up to 1. And then since we have done that, we now have scaled values. So we no longer need our previous columns for time and amount. So now we then use the drop function from the pandas library to drop the amount and the time. And then since we now have scaled amount, we no longer need them, so we drop them. So now we then assign scaled amount. We then assign this variable scaled amount is equals to the column scaled amount. Scaled time is equal to this column scaled time. And then we then drop the scaled amount and then scaled time. And then we then insert 0 for scaled amount and then 1 for scaled time, right? And then we then use df.head to print the first 5 items in our dataset. As you can see here, we now have scaled amount and scaled time, and as you can see, our values are now scaled. So our values are now in the same range. As you can see, all our features are now in the same range, from scaled amount, scaled time v1 up to v28. They are now in the same range. Now, right. So before we go on to perform random undersampling, right, what we do is we need to split our dataset before we perform random undersampling. Why? So for testing purposes, we don't want to test on our dataset, on a subsample that is created by random undersampling, right? We want to test our algorithm on the original dataset. So what we are doing is, when we are training our algorithm, we are going to train our algorithm using the data on the random undersampling technique, or using the data on the subsample that we will create using random undersampling or oversampling technique, right? But we want to test our algorithm on the original dataset, right? On the original distribution of our dataset. Okay, so now we are going to import from sklearn.model selection. We are going to implement the train test split, and then from sklearn.model selection we are going to import the stratified shuffle split, right? So we are going to print the number of non-fraudulent transaction and the number of fraudulent transaction here. And then we are going, since we are only dealing with features, sorry for that. Since on our training features, we want to train our dataset on the features. So we are going, our training set or our features, our features x is equal to df.drop. We need to drop our class, the class which is our label. So we are going to drop the class column, and then for our labels we are going to assign the class column, right? So now we then use the stratified k-fold. So if you don't know what stratification is, a process whereby we rearrange our dataset so that each class, so that our dataset is the overall representation of all the classes, right? So in this situation, we want our dataset to have the overall representation of the fraudulent and non-fraudulent transaction. So that's what stratification means. But stratified k-fold, what it does is first rearrange so that we get the overall representation of our dataset, and then it splits our dataset into k-folds, right? Let's say if we have if k is equal to 5, that means that we have 5 folds. The first thing we do is we train our dataset on 4 folds, and then we use the other remaining fold for testing. After that, we then take that fold that we used for testing, and then with other three folds, and then we take another one that we used for training, and then we'll be using that for testing. Okay, so here we have stratified K fold. The number of splits is equals to 5, which is saying that we are going to create 5 folds. Random state is equals to none. So if random state is equals to none, then automatically this will use the np.random for shuffling our data set, right? So for train index, test index in our stratified K fold, we then fit to, and then we then split, and then we then fit the x variable, our features and our labels, and then we then print the train index, test index, and then original x train is equals to x.ilog, and then we fit these train index and then test indexes, right? So we then turn our original x train values into arrays. Since our algorithm will be using arrays, we need to turn them into arrays. So original x train is equals to original x train dot values, original x test is equals to original x test dot values. So, and then we see if both train and test set label distribution are similarly distributed. So we want them to have the same distribution. So we use train unique label, train counts label, np.unique original y train, and then we return count is equals to true. And then we do the same for our test labels, and then we print the local distributions. As you can see, label distributions, they are all equally distributed, right? Now we then come on to random undersampling. So what we do with random undersampling is, if we take a look at our dataset, we have 492 fraudulent transactions, right? So what we do is we are going to reduce the number of non-fraudulent transactions to 492, and then we first shuffle the non-fraudulent transactions, and then we reduce them so that they become equal to fraudulent transactions, so that we have an equal data set, we have an equal subsample, right? So here we create a sample, df.sample, and then with the fraction is equals to 1, and then fraudulent data frame is equals to df.log df.class. We use the data frame, and then we use the class item, the class column. If our class column is equals to 1, that means that these are fraudulent transactions. But non-fraudulent transaction, and then let's say if the class is equals to 0, then we select from 1 up to 492 rows. So we want them to be equal to the number of fraudulent transactions, right? And then we then use a normal distribution data frame. We then concatenate the fraudulent transaction and non-fraudulent transaction. After doing that, we need to shuffle our data frame rows. So we use the new data frame is equals to normal distributed data frame dot sample, and then we use the fraction is equals to 1, and then we use the random state to shuffle our data set, and then we then use the new data frame dot head, we then use the dot head from pandas, and then as you can see, now we have a subsample with equal number of distribution for both non-fraudulent transaction and fraudulent transaction, right? If we print the distribution, as you can see, it's now 0.5s to 0.5. We can see that we now have the total number of equally distributed classes for fraudulent transactions and non-fraudulent transactions. So guys, this is the end of the video. This is the end of part 1 for using machine learning for detecting fraudulent transaction. So in the next video, we are going to take a look at how our features are correlated, and we are going to take a look at another technique that we use that is called random oversampling, where we increase the minority class so that it becomes equal to the majority class, right? Thanks for watching, guys. If this video helped you a lot, please click the like button and share the videos with your friends. Thanks for watching, guys.